Okay. By the way, it's funny, so you guys are a smaller section in the class right after this. As soon as I ask you all for a volunteer, there's almost immediately a volunteer. Other class has twice as many people, and I ask, and it's like crickets. It's just no one's on quantity. Exactly. I've often noticed, by the way, this is very normal. Sorry. When I have an earlier and then a later section, the later section is usually more full. The earlier section often tends to do better. Maybe it's something about students who are willing to get up at 9 o'clock or for a 9 o'clock class. So, all right. So your next assignment is due tonight, the first class in the higher order functions. Let's begin with any questions that you have about that. Yeah.
So in the previous lab, when we had like auxiliary functions to help with the recursion,
right,
there was like a little note in like the lab spec that said like if you're doing a helper function, then you might need a helper function for the higher order one too.
Right. In some cases, but not necessarily. So if the purpose of that auxiliary function or that helper function was to do, say, another recursion, it's possible that could be collapsed down to one higher order function.
Okay.
So you might need if you had a helper function, you might need another helper function, or you might need another higher order function. I don't know, sorry, my system's been giving me alerts like that. So it might be that you would, again, need another helper function or another higher order function. And you can, of course, have higher order functions that use other higher order functions.
Right. So for like average, you're supposed to be, so previously you'd be keeping track of the depth and then you'd, like essentially undo the average, add the new thing, and then divide it by the new count?
You can, but that's a lot harder.
Right.
The easiest is just sum them all and divide by how many there are.
Okay.
Right? So going back to just the very definition of average.
Right.
Well, sum is an easy fold.
Right.
In fact, I used it as kind of a prototype example. And then length you can use.
Okay.
So
Gotcha.
that's the easiest way to do it.
I didn't know you could use length, so that.
Yeah. Or you could also do
Calculate your
another fold to get length.
Right. Okay.
It would look a lot like sum. You're just always adding one instead of whatever the value is. And so that's where you could use one higher order function call to get the sum, one to get the length, and then just divide.
Gotcha.
Any other questions? Yeah.
For when you eliminate larger, the best thing to do, right, is to fold on the rest of the list.
Yes.
And then see if you prepend the first element.
Right. So back when you were doing the recursive version of it, I made the suggestion in both classes that you may want to, instead of trying to take the first one and make the decision about whether it's going to end up in the list or not right away, recursively eliminate larger on the rest, and then try to make the decision about whether that first one is going to go in, going to get added on or not. The reason is you've already, well, what comes back from eliminate larger, you may have noticed, is in sorted order. And it should be, because otherwise you'd have something with something smaller later. Right? And also if you are comparing, if you're going to see if that first thing is bigger than any of the things in the rest of the list, you really only have to make one comparison against the smallest thing in the list. Right? And that was always at the first of the already recursed on rest, if that makes sense.
Yeah. Okay.
So if you turn what I just said into bracket, that's basically how I would try to code that, okay, with a fold. Anything else? Okay, hopefully you saw my note on Piazza about when you're doing convert, you do not need to compute powers of 10. If you think about the structure of the recursion, just think about, I have the first, and then what would the already converted rest look like? And then look at the mathematical relationship between that and what the answer should be for the whole list. So take a look at that note if you didn't see it already. Any questions looking ahead to Friday's assignment? Sorry, just to calibrate, how many have already finished the first or the one due tonight? Okay, so most, okay. That explains the relative lack of more questions. That's part of why I asked that. And then, any other questions from those of you who've already finished this, or even if you haven't yet, looking ahead to the next one, any questions? Okay, yeah.
Is it going to be similar to, for the decorators, is it going to be similar to what we did with currying on the last function?
Somewhat, in that in the end, you're going to just simply call the function that's passed in.
Okay.
So in that sense, it's a bit like curry2. In fact, you can even think of curry2 as a very simple form of a decorator. It's just that the decoration it's layering on is a one parameter function, another one parameter function, another one parameter, well, just two in that case. And then at its heart, it's just making a call to the one function.
Okay.
You're only going to be adding one layer on for each of the two parts, and then there is a part where you actually layer the two together.
Okay.
So take a look at the examples that were in the notes distributed for that class. I got you through some of them. There's a lot more examples, including other ones with variable parameter functions and things like that, or variable arity. I strongly recommend taking a look at that. All right.
I have a question.
Yeah.
For the currying function, I don't see how it would be used, because it's like inside of it, we generate two types that don't have a value.
Right, but you're returning that function. So you're returning a function which when called returns a function which when called calls the two parameter function. And so, yeah, it's returning it anonymously. And just like any other anonymous function, it's up to the user then, or the caller, to then use that in some meaningful way. It could give it a name, store it, use it right away, whatever it would do with it. Does that make sense? So your job in curry2 is just to create and return the function. Likewise, for the next lab, for the decorator one, you're just creating and returning the decorated function. Now, of course, you're going to want to have your own tests on that. But all that your code, the decorator code does is creates and returns the decorated version of the function. And then the tests and other things will use that. Did that address your question? Did I understand
Yeah,
correctly?
that was helpful. Thank you.
Okay. All right. So last time we started on Julia, there's a little bit more that I just wanted to show you. And then today, we're going to kind of step back from coding for a bit. And we're going to talk about the general structure of programming language tools. It turns out that interpreters, compilers, type checkers, JavaDoc, Doxygen, if you've ever used that, all kinds of tools like that, even code that formats your other code, editors that do automatic formatting and things, all these actually have the same structure. And so we're going to talk about that today. We're going to do that as more of a whiteboard discussion. Before that, though, just wanted to show you one more thing with Julia. So towards the end, we got to the idea that Julia has a type hierarchy. So every type in Julia has a parent type. Okay. So this is the type hierarchy for numbers. So by default, integers default to N64, which is a subtype. Think of it kind of like subclass, but it's not object-oriented, but I'll show you in a little bit that you can basically do everything that you can with object-oriented. So an int64 is a subtype of signed values. That's a subtype of, it's a subtype of signed integers, which is a subtype of integers in general, which is a subtype of real, which is a subtype of number. And then, of course, you also have, it actually has complex values besides real. You have the different forms of integers. You even have rational, irrational, abstract floats. So you've got, also, by the way, you've got signed and the different signed integers and unsigned integers and all the different bit lengths. So one of the things about their type hierarchy is that you can use a subtype as one of the parent types. So for example, if I write a function that takes a parameter that I've declared as real, I can pass to it anything within this hierarchy that falls under real in the type hierarchy tree. Again, same kind of ideas that you're used to with parent classes and subclasses. Now, besides number, there's a lot of other types that it has built in. Strings and all kinds of other things. Sitting at the top, very, very top of that hierarchy, and we just had the chance to touch on this at the very end last time, is a type called any. So this is Julia's equivalent of, you know how in Java, so in Java, every class extends another class. And whether you declare it that way or not. Every class extends another class, and sitting at the top of the class hierarchy is java.lang.object. Okay? And if you don't declare that a class extends some other class, it automatically fills in that it extends java.lang.object. Julia works the same way with its type hierarchy. Its equivalent of java.lang.object is the any type, and anything can be type promoted to any. Now, if you declare a particular variable to be of type any, it means I can put any type in there. So if you actually do not declare the type of a variable or of a formal parameter for a function, it looks like it's kind of typeless, somewhat like Racket, the way that you just don't put types on parameters. In Julia, you can put types on parameters and variables, but if you choose to, it's not that it's typeless, it actually has a type. It's just by default, it fills it in with type any. Does that make sense? So with that, let's go back
So
to,
on that,
yeah,
back to the tree thing,
yeah.
so shouldn't any be at the top?
Yeah, this is only the number sub-hierarchy. It'd be really tiny print if we tried to do all of it on one slide. So I just wanted to give you the basic idea. So imagine that, yeah, sitting way up there is any. Actually, it's barely above that. It just gets really broad from there. So if we go back to some of the code that I was showing you, at the end I was showing you how you can declare structures. So structures are an aggregate type. It's the keyword struct, kind of like in C++. I can declare, let's actually go up here, sorry. So actually, let's back up to here. So for types, I was showing you last time that you can, I could declare functions without putting a type on the parameter, or if I choose to, the way I could put a type on it is the variable name, : type. So this says x takes any int, which is that integer part of it, and adds 1 to it. So if I call this function with 3, that works just fine. Now, you may remember there was a function I showed you earlier, a very simple function f that also takes a parameter x, but I'm not declaring a type. So this one I can actually, it defaults to type any. And so I can call this, I can call h, which takes an integer with 3. If I call the, if I try to call function f, that would work with any, and I pass 3.2, that will also work. But if I try to call h, and I've commented this out here so this part doesn't crash, if I try to call this function h with 3.2, that's an error. Do you see the idea? Now, remember I mentioned type promotion. If I have another version of the function that adds 1 to its input, but it takes type number, I can actually pass to it an int, a float, actually a rational, anything else. that's all part of that number hierarchy. Okay. So what happens then is if I have two different functions with two different type signatures, it's a lot like overloading that you've already seen. I can overload that function to have multiple type signatures. It will try to find an exact match if it can. If not, it will try to look what's the least amount of type promotion that I have to do to find a match. So it basically starts crawling up the type hierarchy till it does find a matching type signature. So in this case, if I've got a function that takes a number and a function that takes a string, it will automatically just simply call the right version of that. Does that make sense? All right. So using that, I was showing you at the end last time, I can define structs. Again, I can have ones that are where I leave off the type. If I leave off the type, it just defaults to any. So in this case, I've got a point that is, I'm calling it my point because point's actually built-in type. My point takes an X and Y, has X and Y fields, each of which are type. Okay. I am sorry, it keeps popping this up. So I can so the way that you create a struct is by simply the name of the structure and then passing it the parameters. This kind of thing, by the way, in many languages is called a constructor. Now you've already seen the term used for object-oriented programming. So for object-oriented programming, I say new, that type, and then I pass it some parameters, and under the hood it automatically calls some function that we call a constructor. In this case, you can think of the name of the struct is itself a function that you can call. So there's no keyword new or anything. I just say p equals my point, filling in x is 3 and y is 4.2. You see the idea? Now 3 is an int, but I can set this to it because it's a real. Same way if I had an object that had a field that was a float, I can initialize it with an int and see. Yeah?
Are there default values?
There are not. You have to actually give it, when you build it, you have to fill in all the parameters. Okay. If you want a function that will fill in default values, then basically you would write it yourself and then call that to create. Okay. But inside, it has to be built with all of the fields initialized. The way that you access elements is just simply with dot notation, much like you used to in C. So if P is a point which has subfields X and Y, I can do P.X and P.Y, and that will print out what the fields are, okay, or what the elements are. Now, you can actually create your own type hierarchy. It's somewhat restricted. It's not as extensive as its built-in one. But the way that you can do this is if I want, say, 3 different flavors of points, which take, say, int fields, real valued fields, and unsigned int fields, I can just simply declare them. But what I can do is declare that these are all considered part of the same type. The way you do that is to say abstract type, the name of sort of a parent type, if you will. By the way, it has this abstract keyword, so it's like in C and C++, or like C++ or Java, you can't actually create one directly. You can only initialize sort of the concrete versions, not the abstract. So I would say, though, that I have this sort of abstract type, my point. By the way, it's abstract type, my point, and then end. You have to actually finish that off. But then you can say, sorry, you can actually put fields here. So you can actually say abstract type, my point, some fields, and then an end. I just ran it all on one line. That's usually what I do if there's no fields. So in this case, notice the notation here, less than colon. This is indicating a subtype. So struct int point is a subtype of my point with these fields. Real point is a subtype of my point with real value fields. Uint point is a subtype of my point with uint fields. You see the idea? And so now I can create concrete instances of each of these three types of structs. And when I call functions with it, it uses a mechanism called dynamic dispatching to basically dispatch to the, in other words, call the appropriate version of the function based on whatever type something actually is. So even if something's declared to be a parent type, it will automatically dispatch to whatever child type it actually really is. That should sound a lot like virtual functions in C, or virtual methods in C++. So I could have a function show point that takes an integer point and prints it out, or prints out that it was called, or a real value point. And so if I pass, if I call show point with P2, which was integer valued, it calls this one. If I call show point with P3, which was real valued, it calls this one. If I show it with P4, now P4 was the unsigned int one. Which one does it call?
Top one.
Yeah, it doesn't find a match here, and will eventually go up to the myPoint class, and it will, sorry, type, myPoint parent type, and it will print out this one. You see the idea? Okay. All right. By the way, if I declared something, if I do something like this, P5 equals so, well, sorry, I want to actually clear. If I had something that was I could declare something to be a myPoint, and if I assign to it the result of constructing some actual real or integer or unit valued one, it will dispatch to which one it actually is, not what it's declared to be. You see the difference? Like I said, that should be what you're used to with virtual methods in C++ or all method calls in Java. You may notice that the combination of these, the dynamic dispatching plus subtyping, in essence gives you everything that you're used to with object-oriented programming. In the sense of inheritance, in the sense of functions that know how to operate on certain types of data and are appropriately dispatched. The one thing that you don't have is that the declaration of the data and the declaration of the code that manipulates that data is packaged together. Now it has the notion of a module, and I'll show you that when we actually start coding more. You can define a module that exports certain types and exports certain functions that work on those types. So together you actually have the same kind of capability you're used to with object-oriented languages. But the nice thing is, if somebody else wants to start creating functions that operate on that type, you don't need to go back to the source code that declared all those methods and add one more method to the actual class declaration. You just create another function that operates on that type. And it automatically just becomes part of of the functions that can work with that type. A lot of languages are going that kind of direction. Even though we show you early on, object-oriented programming is the one true way, it's not actually. Sorry, don't tell Dr. Rodham or Dr. Woodfield I said that. There are lots of other ways. You've seen functional. There are attempts, by the way, to blend functional and object-oriented. There's extensions to the notion of object-oriented of all kinds of things that add in what are called mix-ins in some languages. Any of you ever heard of something called duck typing? The sort of notion is it's a way of it's another variant of kind of object-oriented programming, which is basically even if that thing isn't declared as part of that class. The reason it's called duck typing is if it walks like a duck and sounds like a duck, it's a duck. So the idea is if it behaves like that class, you can actually use that class. And so be aware, there's a lot of other things. We're going to be using dynamic dispatching a lot actually in our interpreter that we're going to write. So let's take, yeah.
Julia is a compiled language.
Yeah, it's going to look and act like an interpreted one, but under the hood it's compiling and caching things. So when we start actually working with our own modules and we start changing code, you might notice little warning messages that say recompiling cache. Right? And those are just letting you know, hey, I'm actually going ahead and reloading this stale cache for you. But yeah, it's compiled. All right. So let's take our last time and talk about just sort of what programming language tools all about. Sorry, I'm still fighting respiratory things from all the smoke in the south part of the valley. All right, so let me ask you some questions. What's that do?
What language?
Exactly the right question. In what language? Right? So in a lot of languages, this is accessing an element of an array. Is it accessing the second or the third one?
Depends on if it's 0 indexed or 1.
Depends on what indexing it's using. Right? What does that do?
Depends on the language.
Depends on the language. You guys are getting this. So what could it mean?
Assignment.
Could mean assignment. A equals B, so it's assignment. But now if I modify B, does A change or not?
Depends.
Again, it depends actually on the language, right? And in some languages, it even depends on which type you're talking about. In things that derive from Algol, which include Pascal, Ada, Module 2, things like that, this is a comparison operator. Instead of using equals equals, it uses this for is A equal to B. And then use a different colon equals for assignment. So one of the things that you've probably seen that's tricky in different languages is what might look outwardly the same might actually mean different things. And so we talk about the syntax of a language and the semantics of a language. Syntax is form. Okay? I often describe it as how do you have to format your input to make the compiler stop complaining about missing semicolons and other kinds of things like that. Right, so it's the form in which you have to type things. Semantics is the meaning. And so what we've seen with this is you can have things that look syntactically similar, but have very different semantic meanings. That's probably the toughest part about going from Java to C++ or vice versa, is that you actually run into a few things that look the same syntactically, but are different semantically. Have you ever been bitten by that bug? Okay, or bugs like that? Okay. So I can have things that look the same syntactically, but have different semantics. Similarly, I can have things that have different semantics, or sorry, the same semantics, and look different syntactically. Sorry, let me just actually do this. Something here. All right, so these are 3 different languages. Anybody recognize the languages? Yeah.
The second one could easily be Lua.
Yeah, Lua and
script.
pardon?
Even VB script.
VB script. All those Algol variants, so Pascal, Ada, Module 2 extensions like that, or derivatives. if you leave this part off, Julia, pardon?
Not quite.
But it has to have a new line. This one,
JavaScript.
you should all recognize.
JavaScript.
Yeah. Pardon?
Oh,
Yeah.
you just said JavaScript, but it could also be like C or C.
Yeah, it could be C, C++, Java. This one is a language called ML. A greater than 3 implies this. Okay, so it's the same as if this, then that. If you look at what they have in common, they all mean the same thing. Evaluate the test to see if A is greater than, oops, sorry.
I was gonna ask
Now
if that
they
was.
mean the same thing.
No, the bottom one is.
Thanks.
Okay.
I changed the wrong outlier. All right, now they mean the same thing. So all of these just simply say there's some test that I'm going to evaluate, and if that's true, I'll execute this. Execute or evaluate and return. Okay. So semantically, they have the same meaning. All you really care about when you actually get to the point of implementing an if is if you just simply say, what's the expression I need to evaluate for the test? What do you want me to do if that's true? And what do you want me to do if that's false? Right? All the rest is pure syntax. This syntax actually predates the C-style syntax, okay? Using actually a keyword explicit, keyword then. Actually, in some cases, you'd actually have to even do something like a do. So Pascal actually has this. Do and end actually match up. In C++, you're used to those as curly braces. So this is for a block. Why do we put parens around the test in C++? Have you ever wondered why do we have to put parens around it?
Because they said so.
Because they said so. Okay, so that's part of what you as a language designer get to decide. Right? But why, especially this one, why is this one? This one actually is totally meaningless. This one just looks pretty. Right? Because you already have the keyword if before it. What's this one do?
Ends the
Yeah.
question.
It tells you when the expression for the test, when the test expression ends, and then the part that you do if it's true starts. It's purely a terminal in the grammar. Hopefully you know what I mean by that, but we'll come back and talk about it. It's simply there to tell you when one starts and when it stops and ends. So I could use then, I could put parentheses around it, I could use an implies signal from logic, or an implies symbol from logic. All of them work to simply separate the test and what you do if it's true. That's often called the consequent. So what we want to do first when we're actually working with it is when you go to actually interpret an if statement or an if expression, depending on which one you're doing or both, the first thing you want to do is say, look, I recognize from the structure that it's an if. Let's just boil away all the other terminal symbols and sort of cruft that's there just to keep parts separate. Let's just figure out, what do you want me to test? What do you want me to do if it's true? And then if you have else's, what do you want me to do if it's false? Okay. So let's just boil those parts out and keep them. And so, So this gives rise to the notion of what's called abstract syntax. So the abstract syntax is simply data structures that store the structure of your code without all the little terminal symbols and things. Now, so we talked about syntax and semantics. So going back to this for a minute. If I want to give you a new language, how can I tell you what the syntax is? Remember you said because they said I have to, right? How do I tell you what the syntactic rules are?
Documentation.
Okay, documentation. Yeah, we don't read the documentation. No, but yeah, you
Compiler
have to
errors.
document it, right? But what form would you document it in? Yeah.
Like a grammar.
A grammar, okay? So you've all seen grammars in 236 and then 252 if you've taken it, right? So grammars are a way of writing syntax. A little bit of history here. Remember I mentioned sort of early days of computing. You have sort of Fortran, Lisp, COBOL, and one of the languages to emerge around that time also was one called Algol. Now if you actually look at the structure of, if you actually look at the syntactic structure of Fortran or COBOL, they are absolutely hideous. And the reason is they started off basically saying, let's just write a compiler. Let's write a compiler for this new language, and we'll just sort of make up the form that things have to be in as we go. Algol took a totally different approach. They said, wait a minute, there's this notion of formal grammars. Let's actually write out a formal grammar first, and then let's start working with from that. Okay. So the notation that you've seen for grammar is called Backus-Naur form, or BNF. Did your instructors in 236 ever call it that? Okay. So, sorry, I'm curious, did they, or?
It's been a while.
Okay. All right. So that form that you've seen, this non-terminal can be defined as, that's all Backus-Naur form. And so Backus and Naur were the leaders of the Algol 60 project. Yes, circa 1960. And so if they said, all right, we're going to use formal grammars to actually define the grammar of the language first, we need a notation for writing grammars. And so the BNF, that notation that you learned in 236 and 252, is BNF, or Backus-Naur form. So that's one way to communicate syntax. What about communicating semantics? How do you tell somebody what those different constructs, sorry that I unfortunately erased a moment ago, mean?
Say the function definitions.
Yeah, I mean, I could write out, you said it's in the function definitions.
Yeah, like what equals means, what equals rules means.
Right. So I can document what they mean. So one way to do that's in English, or pick whatever your other favorite language is, with all the vagaries of human language. You ever thought you knew what something meant in a language after reading a description and then found out it really wasn't quite what you thought it was? Right? So human language is always vague in some points. There's just things that may be left out and then added and added and added later. Another way, by the way, is there's all kinds of formal ways with sort of axioms and proofs and deriving things, which gets ugly. But it's one other way of doing it. Another is to actually build a working interpreter or compiler. It doesn't have to be fancy. It doesn't really have to be entirely bulletproofed. It doesn't have to give you great error messages as long as it catches errors. It doesn't have to be efficient. All it has to do is function the way that you want the language to function. And then if someone says, what does that do? It does what that prototype example interpreter compiler do. Okay? This is sometimes called operational semantics. All right, so let's go back to this idea of syntax. I have this form of it. I'm going to erase this now. The form that you actually type things in text is called concrete syntax. Did they ever use that term in 236, just out of curiosity? Because you did some very simple parsing there, right? Okay. So concrete syntax is it's the grammar, right? It's how you have to type things in. But remember I said the first thing that you want to do is actually go through and parse all that out. You know about grammars and parsing, right? So you parse it out, but in the process of parsing, you throw away all the terminal symbols. You throw away the parentheses around things. You throw away the then and the end and the do and all these other keywords. Pascal has begin and sorry, do is actually a different language. Sorry. Pascal has begin and end. C has open curly brace, close curly brace. Who cares? It's start a block, end a block. Okay? And once you figured that out, you don't have to keep those keywords around. So the job of a parser is to turn things into abstract syntax. So hopefully you saw the notion of abstract syntax in 236. Right? Did you create what are called abstract syntax trees or talk about those?
I don't remember.
Okay. I'm going to have to talk with my friends to teach 236. All right, so the idea is an abstract syntax is simply a data structure that says they're doing an if, here's what you do for the test, here's what you do if it's true, here's what you do if it's false. And you throw away all the non-terminals. So the abstract syntax throws away all the non-terminals, and it preserves the structure of the operation. So I might have something that just simply, and it stores it, by the way, as a tree. Anytime there's a non-terminal in the grammar, that becomes a subtree within the abstract syntax. So I could have something that says, here's the f, or the test for the if, and maybe it's a less than operation with a and 3, and then what I do if it's true is this, and what if I do if it's false? It's something else. Okay? So you end up with a tree-like structure that can be quite deep, depending on how deeply you nest your expressions. So this is the abstract syntax. So when you, so the first thing a language tool will do is parse all the input and turn it into abstract syntax, these abstract syntax trees. Usually it's one tree because these are all part of one program or module or something like that. So have you any of you ever used, I know Perl does this, I think some implementations of PHP do it. You ever worked in an interpreted language where you have an error on line 603, a syntactic error, and you start running it, and the first thing it complains about is the error way down on line 603. It doesn't run all the other 600 lines before that. What it's doing is it's taking your entire code, parsing it first, and then it will start running it. Now here's why you do this. Suppose I had some complicated expression in the middle of a while loop that's going to repeat 10 million times. Do I really want to go through re-parsing that text 10 million times every time it loops through? So when you first learned interpreters, it was probably, it reads each line and then executes it. Well, actually, not quite. It does the equivalent, but it doesn't actually read the text over and over and parse it over and over every time you're looping through, or every time the body of some function is called. It does it once. And then after that, it just traverses that abstract syntax tree, evaluating it 10 million times in that loop. You see the idea? So once you parse, so the job of a parser is only, and I repeat, only to go from concrete syntax to abstract syntax. Do not stick anything else in here. Now there are some things it might throw out, like comments and white space and stuff. But otherwise, its job is only that. Now in the middle of a system, you're going to have some sort of translator. The translator's job is to go abstract syntax in and abstract syntax out. Now this might seem kind of odd. Why convert it to abstract syntax? Well, the idea is you're turning it to the abstract syntax of the form you want the output to be. So this is the abstract syntax of the input. This is the abstract syntax for whatever your output's going to be. Then what you do is you say to something, take that, and you feed it into something called an unparser. And it actually produces your output. So we're almost to the end, but I want to run through some quick examples with this. So what if I have the same abstract syntax here and here, and I just leave the translator out? I just take this, feed it right into the unparser. If I can parse to turn it into abstract syntax, can't I traverse that abstract syntax and turn it back into text, concrete syntax? I mean, I should be able to go both ways, right? Except what would happen? What would be lost in the process? Yeah.
Maybe white space.
White space, comments, other things like that. But as I'm traversing this, I could actually keep track of the depth of blocks and net loops and things like that, and I could automatically reformat it to nice looking white space. Any of you ever use what are called pretty printers or code beautifiers or anything that will take your ugly formatted code and turn it into nice, clean, indented code? That's all it's doing. It's just this. All right, last things to think about, and we'll pick this up next time. What if I put in here a C++ compiler? So I parse C++, I compile it not directly to machine code, but to some abstract form of sort of a generic kind of machine code. And then I parse that to actually pack all the appropriate bits for the actual binary codes. Right? What if I now change and I want to target a different CPU? What changes? Just this, right? Sometimes called a code generator. JavaDoc, parse Java, turn it into an abstract representation of your HTML document, unparse that into HTML, and then, oh, by the way, that's going to get reparsed and laid out nice and clean on the screen in your browser.